Okay, this is video number 16, Forces Part 2. In the previous video, we defined what forces are and introduced the idea of a free body diagram, which is a tool to help us add together vector forces. In this video, we're going to practice free body diagrams and talk a little bit about the terminology you'll need to use to identify various forces that you'll come across throughout this course. So we started in the previous video talking about this experiment where we had multiple forces acting on a cart, and so the cart did not experience a delta V. And we had to reword our law of inertia to reflect that multiple forces acting on the same object could be adding up to a vector sum of zero net force, which would give you then zero delta V. So not every force acting on an object causes that object to experience a delta V. We talked a little bit about how you would want to use this type of diagram that we call a free body diagram, or sometimes called a force diagram, to show how the forces add together. By drawing them like this, I get to see that the force of the track holding up the cart is acting in the exact opposite direction of the force of gravity pulling down on the cart. And so I can see pretty immediately that they are working against each other and possibly would add up to zero. So a diagram like this is especially helpful when you know the forces that are acting and you know what some of them are equal to, and you don't know what all of them are equal to, and you need to figure it out. So throughout the universe, physicists would say there are four fundamental forces in our universe. These are the only four forces that we know exist. The gravitational interaction between any two objects that have mass, the electromagnetic force, which is actually the third one over on this chart. That's actually the entire focus really of physics 150, and it tells you that any two objects that have electrical charge will push or pull one another, and if a charge moves, it creates a magnetic field and a magnetic force. But that's in physics 150, so we don't really talk about it here. The electroweak force, or the weak interaction in particular, has to do with radioactivity, causing objects to undergo radioactive decay. And then the strong interaction is what holds together the nucleus of an atom, keeps the protons and neutrons held together. None of these, besides gravitational force, are terms that you're likely to actually use. So if these are all the forces in the universe, and the only one of these that I said you're going to probably use is gravitational, then that clearly needs some investigation. What else are we dealing with if not these four forces? And the answer is almost every interaction you have with objects around you is some manifestation of the electromagnetic force. Other than gravity, every interaction that you're having is electromagnetic. Let me explain. We have the term tension. The force of tension describes a pulling force that is conveyed through a rope or a string or a cable or a spring. But really what the tension force is the aggregate of all of the molecules in the rope holding each other together. And so when you pull on a rope, the rope molecules pull on each other, and eventually down at the other end of the rope, that pull is conveyed to some object. I want to mention tension because it is equal throughout a rope or string or cable or whatever. So like you see here on the right, there's a force of tension pulling down on the hand and a force of tension pulling up on the mass. If your hand is holding this rope and this rope is holding this mass and you're just holding it there, you'll feel a downward tug. You'll feel how heavy it is how we usually think of it. That downward tug on your hand is the force of tension, and that is equal in magnitude, just opposite direction, from how the mass experiences that same interaction. The mass is feeling the rope pull up. If you put a heavier object on there, you have to pull up harder, and you feel it pulling down on you harder. We'll get more into that, but for now, anytime you see a rope or a cable or something like that, you can call it the force of tension. And anytime a problem says that a force of tension is involved, you can interpret that to mean there's some kind of string or rope or something like that. When two solid objects are in contact with each other, the point of contact is a force that we refer to as the normal force. It is just the force that is preventing two solid objects from passing through each other. So if you don't pass through something like a ghost, and you actually make contact with it, then you're experiencing a normal force. It's called that because it is a mathematical term that means a direction that is perpendicular to a surface. So for example, in the image here, you have this vector n1 pointed up out of this yellow rectangle and vector n2 pointed down. These are what mathematicians would refer to as normal to the surface. You could say perpendicular, but when you say normal, you're being a little bit more specific and you're saying this one vector is perpendicular to this entire plane. So the force normal is a force that acts perpendicularly to the surface that you are contacting. And as it says here, it's the aggregate result of solid objects being held together by molecular bonds. When your hand makes contact with a solid object like this, it doesn't pass through because the two objects are held together at the molecular level by their own molecular bonds. It gets a little bit interesting when a surface is curved, and I won't spend a lot of time trying to trick you on this, but if an object does have a curved surface, you need to know that the force that is the contact force would be normal at the point where the two objects are actually touching. Your textbook explains what the normal force is, or the force normal, by showing that here on the left, there's this bag of, what does it say, Bow Wow Chow? That's what they're calling the dog food. And when it's being held up by hands, gravity is pulling down on it, and the hands are pulling up on it, and so the bag doesn't go anywhere. Then when you put it down on the table and you let it go, and you walk away, it hopefully is held up by the table. The force of gravity is still pulling down on it, but it's still not falling. Something is exerting an upward force on it. And when you look at a bag of dog food sitting on the table, you probably don't think of it in terms of the table is pushing on it, because the term pushing kind of implies that it's going somewhere, but the term pushing should not imply that it's going somewhere. It just means that they're in contact with each other and not pulling. So this table is holding up this bag of Bow Wow Chow, and the way that it's doing it is what we would refer to as the force normal to the surface where the two of them are in contact with each other. I don't like how OpenStax refers to the force of gravity as the weight, and especially don't like that they call it W here. And I'm not a fan of the fact that they're referring to the force normal as just an N on the free body diagram. I very strongly encourage you to use the capital F subscript, whatever the term is that you're going to use, for reasons that will become more obvious as we go throughout the course. The short version of it is that W already means something in a later chapter, so making it mean the force of gravity here is not very clear. It's not a good idea. All right, we are to our first practice free body diagram. For the next, I guess, 3 questions here, I'm going to give you a scenario, a picture, and I'm going to describe it. A string is tied to a book. I pull upward on the string. The book does not move. It remains in contact with the table. And it would be a good idea to pause it if you have some idea of how to draw the free body diagram, and then compare your free body diagram to the one that I draw, which is coming up right here. So if you haven't paused it, pause it. I start out with this little rectangle. I said in the previous video that you could make your object a dot or a box or something for your free body diagram. And what I want to do is I want to start with any force that I know is acting on this book. I know that gravity is acting on this book. It's pulling down. So I'm going to start with that one. That is almost always the best one to start with, because you know that the force of gravity is pulling down on everything. I would have to give you a really contrived situation where you're out in space between galaxies or something where you wouldn't really, even there it acts. So force of gravity is usually a good one to start with. And you know what direction it is. It's straight down. What else is happening is there's an upward force. I don't know how strong the upward force is, but the force of me pulling up on the string, I could call it the force of tension. Instead, I called it force of string here. I know that it's not enough to overcome gravity because the question said that the book hasn't lifted off the table. So I'm pulling up with an upward force that is not as strong as the force of gravity. This can't be it, though. There has to be another force, because these two arrows are not equal size. And just by looking at it, I can see there's a net force down if these are the only two acting. And that would mean the book is falling. What's keeping the book from falling is that the table is interacting with it. It's providing an upward contact force that we could refer to as the normal force. Here I put it as force of table, but calling it a normal force would be a good idea. I drew that one last because it really, how strong the normal force is dependent on how strong the force of the string is. The two of them together should add up to an upward force that is as strong as the downward force of gravity. They should, because I know that the net force on this book is 0 because the book's not moving, so it must have 0 delta V. All right, let's try a slightly more complicated one. There's a book on a table, and I'm pushing straight downward on the book. I guess in the picture, I've had students tell me in the past it looks a little bit like there's a rightward push here, but there's not. I promise. It's straight down. So maybe pause it and try to draw a free body diagram for this scenario. All right, I have that the force of gravity still exists and will be pulling down on this book. How big do I make the arrow? I don't know, so I just draw a downward arrow and I say this is the force of gravity. I don't know how strong it is yet, so I'm just going to show the direction and label it. I know that the book isn't falling, and the reason that it's not falling is because it is in contact with the table. So this looks like a good start. I've got the force of gravity pulling down and the force of the table pushing up. But I've got the force of the hand pushing down, possibly more than the weight of the book, possibly more than the force of gravity. And so by this drawing, it would look like there's a net force down and the book is falling. This is why I would like to draw that interaction between the table and the book, that normal force, last. I don't know how strong it is until I know what's going on with these other two forces, the gravity and the hand pushing down. Now I know to draw the normal force much bigger so that it is approximately equal to the hand and the gravity magnitude combined pushing downward. So these three look a lot like they might add up to 0 net force, which is what the book is experiencing. All right, let's take a look at this slide. It says free body diagram complications. I'm sure you were thinking, really hope he makes things more complicated. We have two books stacked as shown, and we have the request that you sketch and label a free body diagram for each of the books, the upper book and the lower book. So go ahead and give that a try. All right, here's what I have. The upper book has the force of gravity pulling down on it. So I'm going to start with that. I'm going to say the force of gravity, parentheses, U. And the reason I want to put parentheses U is because I'm going to have a force of gravity acting on the lower book also, and those two are not going to be equal. When we are putting these free body diagrams together, the point is that we will then use these to help us calculate actual values. So if I know that these two values are not equal, I'm going to want to give them at least a little bit different names. The upper book is not falling, so something must be holding it up. And what's holding it up is a normal force, that's true. But specifically what's interacting with it is the lower book. So I'm going to say there's an upward force from the lower book to the upper book. That's it for the upper book. It's just that. The lower book has a little bit more going on. You have the force of gravity pulling down on the lower book. I'm going to make the arrow smaller because the lower book looks smaller than the upper book, so I'm going to assume that it weighs less. The next thing you might be tempted to say is that the lower book feels the weight of the upper book. I'm going to discourage you from calling it that. In fact, I'm going to go out of my way not to use the word weight at all. It's a term that gets used a lot in science and engineering, and it actually gets really confusing when scientists and engineers are using this. For example, your textbook refers to the weight of an object as the force of gravity between that object and the earth. So like your bag of dog food in the earlier example, they referred to it as having a weight pulling down on it. But when you talk about something like, for example, the astronauts going up into the International Space Station, we refer to them as being weightless. Well, they're definitely not failing to experience gravity. They definitely do experience gravity, If you were to weigh them by putting them on a scale, you would get 0 reading, but it's not because they don't have any interaction with the Earth. So they definitely have an interaction of gravity. The term weight gets very confusing in these situations, so I think it would be best to avoid it. Another example of how it can be confusing is right here. If you say the upper book's weight pushes down on the lower book, and let's pretend I don't know what that means, and I think about it and I say, well, earlier you said that the weight of the dog food was the gravitational attraction between the Earth and the dog food. So the weight of the upper book must be the gravitational attraction between the upper book and the lower book. It's not. And if you said the weight of the upper book is pushing down, I know what you mean. I do. But I know what you mean isn't a good way to conduct science. So I would prefer to just avoid the term weight at all costs and use the term force of gravity to talk about the Earth pulling down on an object. The lower book is experiencing the upper book in a contact setting, not in a gravitational setting. The upper book is pushing down on the lower book. I'm going to say that's a contact force because they are in contact. And in fact, I'm going to point out that the amount that the upper book is pushing down on the lower book is exactly the same as the amount that the lower book is pushing up on the upper book. That's Newton's third law. The lower book has one more force acting on it. It is not falling, so it must have something holding it up, and that is whatever that is, the table or the floor or whatever it is. And I'm going to make that bigger so that it looks like it's big enough to counteract the gravitational attraction of the lower book to the Earth, but also that extra pressing down of the upper book on it. So table to lower book, for example. If yours looked like this and had slightly different labels, then that's fantastic. If you had no idea how to draw these and you didn't try doing them on your own, then I hope this at least gives you some idea of how to do them. But we still want to talk about why we would do them. All right, let's take a look at this problem here. We have two people attempting to move a large block. The block is not moving. Chris is pushing the block. Pam is pulling on a rope attached to the block. I want to identify all the forces that are acting on the block and label them. So the first one I would put is, as usual, I'm going to say there's a downward attraction by the Earth. It is a gravitational attraction. The next one I'm going to put, I think I'm going to look at this and say, how about this pull to the right? This is the force of Pam on the block, or you might call it the force of tension. What you don't want to do is count it twice. So if you call it the force of the rope on the block, don't then in addition to that say the force of Pam on the block. I'm telling you that because that's something people do. The next force I want to include is, well, if we're counting what Pam's doing, let's count what Chris is doing. I want to be careful, though, not to draw the arrow over where Chris is. It seems like a natural thing to do, but remember, when we're doing a free body diagram, we really want all of the force tails to start in approximately the same place in the middle of the object. This makes it really clear how these two add together. If you draw the arrow pointed into the object, then that is not a correct way to do a free body diagram. There's a few things I do need to be a stickler about, and that's one of them. The force of Chris is to the right, so we draw the arrow to the right, and we draw it emanating from the block, not over at the point of contact. My block's not falling, so I know there must be some upward force that's approximately equal to the force of gravity. It should be exactly equal to the force of gravity pulling down. This is the normal force. This is the ground holding it up. And these are all the forces that I see acting on this block. And I look at this and think, okay, this is a pretty good free body diagram, and maybe I'm ready to start calculating things. But I go back and read the question. They're attempting to move a large block. The block does not move. You might say, well, maybe it's so heavy that they can't make it move. But we said in the previous video that even a really massive object will experience some delta V because you've applied a force to it if that is a net force that is applied to it. So if it's not experiencing a delta V at all, it must have a net force of 0. Something has to be going to the left in this video. And you would probably do okay to guess that it's friction. So I'm going to add this friction force. I'm going to add it very low here because it's happening at the contact between the two. If you're wondering how I added friction, when that hasn't been something we've talked about at all, it's just we're going to throw in friction now. That's a valid point. Let's talk about what these other forces are that we would need to include at all in our analyses. The force of friction is a contact force, so much like the normal force. In fact, what we will learn next week is that it is dependent on the normal force. When two objects are in contact with each other, especially two solid objects that have surfaces that are rough, those rough surfaces might feel very smooth to us, but at the microscopic scale, if they're rough, then when the two objects slide across each other, those jagged edges will interact to try to prevent the two surfaces from sliding across each other. The force of friction is, as it says here, that aggregate result of those interactions at a scale so small that the surfaces do appear rough and jagged even if they feel smooth to our touch. A related force that we don't really spend time calculating in this class, but we want to make sure that we know what it is if it comes up. Fluid friction is sometimes called drag, and that is just the same idea, except it's a solid object moving through a fluid. Fluid does include liquids or gases. We do ignore air resistance, and we don't deal with objects moving through water in this course very much. But it's possible that a problem would come up where you would be talking about fluid friction, and it opposes the motion of an object through this fluid. Occasionally, you'll see thrust and lift used in various problems. Thrust is a really general term we use to describe what a rocket or a jet engine is doing. When they push a gas, especially with jet engines pushing an air backwards, Newton's third law dictates that if the jet engine is pushing the air backwards, the air is pushing the jet engine forwards. And the same issue is happening with rockets. You're pushing gas exhaust out one end of the rocket, and by Newton's third law, that gas is pushing the opposite direction on the rocket itself. So thrust just means like it's some pushing force by an engine. And if you don't understand exactly how it's made, but you understand that it's a pushing forward force, then that's valid for now. Lift is a term that we probably won't use specifically, but it could come up if a problem is talking about an airplane or something like that. And it's just the upward force that occurs as a wing-shaped object is moving through the air. Any of these terms, that the point of all this is, any of these terms could be used on the free body diagram. If I tell you that there's a rocket thrust acting on this object, and you are thinking to yourself, I don't really understand how rockets work, and I don't really know what thrust is. But if you understand that it's a force, then you can kind of put to the side how much you need to know about rocketry right now, and you can establish it is a force that I can put on a free body diagram, and I can make some calculations with it. And if I need to know more about how rockets actually work, I can go back and look at that later. That's possibly more complicated than we're trying to make an individual problem. Don't overthink these. The basic problem-solving strategy for any question that has forces is that we will start with a sketch of the problem, and it says list your known values. There's a special way to list the known values that are forces. Draw a free body diagram to list your known forces and the directions that they go. List things that are not forces separately from the free body diagram, because you cannot add a displacement to a velocity or a velocity to an acceleration. You can't add any of those to forces. So they, even when they're really important to the question, they should not be on the free body diagram itself. Determine the net force through vector addition. That may involve some complications that we've been going through when we talked about how vectors work. For example, if a force is not on the x-axis or the y-axis, it's off at some angle, then you would need to break it into x and y components, which is something we've done with some of the other vectors already. You would then add up all of the forces in the x direction, and you would add up all of the forces in the y direction and come up with a single value in the x and a single value in the y. You could leave it in vector notation if that's appropriate for the question. You can also convert it over to a single magnitude and angle if that's appropriate. Either way, once you have a net force, what you're probably going to do is put it in Newton's second law, F equals ma, to relate the net force to the acceleration of your object. That's what we're trying to do with this strategy right here.